Hi, Chemistry 3111. This is Chapter 12, Alcohols and Phenols. And if you go way back into the second chapter of Organic Chemistry 1, where we covered functional groups, you would have learned that an alcohol possesses a hydroxyl group. Sometimes we just abbreviate it as R and then OH, and we say when we have that hydroxyl group, we have an alcohol. Some common examples of alcohol, well, the most famous of all the alcohols would be ethanol. Its structure is shown here, and that's the alcohol that is found in beverages like a Coors Light. And then we also have this compound here that we would call cyclopentanol. And you can see that what both of these compounds have in common, besides the hydroxyl, is that they end in the suffix -ol. And we're going to see that whenever we name an alcohol, that our alcohol is going to end in -ol. Hydroxyl groups are also very common in naturally occurring compounds. For example, this grandisol, which is found is a sex pheromone of the male boll weevil. You can see that it has a hydroxyl. Also, this compound that's an antibiotic has two hydroxyls. But if you think about a compound that's very common in biology and biochemistry, if you studied cell membranes at all, you would be thinking of cholesterol. And cholesterol ends with -ol. And here's the structure of cholesterol right here. You can see that cholesterol has a huge hydrophobic region here. It's largely a nonpolar molecule. However, it does have a hydroxyl, and so we do refer to cholesterol as an alcohol. Also, vitamin D3 has the hydroxyl group, which renders it an alcohol. And geraniol, if you like the odor of roses and geraniums, this is one of the compounds that makes up the odor that is associated with those plants, roses and geraniums, and it's also found in different types of perfumes. Well, if we put a hydroxyl group and we directly attach it to a benzene ring, we get what is called phenol. And phenol is also one of the focuses of Chapter 12, and you can see that phenols are also found in a wide variety of compounds. Your eye might be drawn to this one down here in the bottom right. This is THC, tetrahydrocannabinol, and you can see that it has a phenol group in it. So this is THC, which is the psychoactive ingredient or component of marijuana. Also dopamine. If you've ever studied, again, if you studied biology before, you might have studied neurotransmitters. And dopamine, when a person experiences a deficiency in dopamine, it can result in Parkinson's disease. Of course, if a person has too much dopamine, that can result in schizophrenia, but there's a phenol in dopamine. What else? Capsaicin, which is responsible for the spicy hot flavor in chili peppers, has a phenol in it. Anyhow, all kinds of interesting compounds that are alcohols and also phenols. Now, how do we go about naming alcohols? It says here that alcohols are named using the same procedure that we used in Chapter 4 to name alkanes, but with a few minor modifications. Let's check those out. First one is it says we want to identify the parent chain. However, the parent chain has to include the carbon that the hydroxyl is attached to. Therefore, if we find the longest chain, but it doesn't contain the hydroxyl, it's not considered the parent chain. It's got to contain that hydroxyl. Then we want to identify and name our substituents, whether they're a chloro, bromo, methyl, ethyl, isobutyl, whatever. Then we want to assign a locant, which is nothing more than a number, and a prefix if necessary. So 3,3-dimethyl, 4-ethyl, whatever, to every substituent. And we give the carbon that the hydroxyl is attached to the lowest number possible. We don't worry about the other substituents. The only thing we're concerned with is giving the hydroxyl the lowest possible number. Next, we want to list the numbered substituents before the parent name in alphabetical order. We ignore prefixes except for iso, cyclo, and neo when we're ordering alphabetically. And then the last thing is that the hydroxyl locant is placed either just before the parent name or just before the -ol suffix. And I'll give you an example of that. Here we go. If you remember how to name an alkane, like a 5-carbon straight chain hydrocarbon, then you would know how to name pentane. And if we put a hydroxyl group on the end, then it becomes a pentanol. Now this isn't the complete name of this compound because we want to number the carbons and we want to give the hydroxyl the lowest possible number. And so we would put it on this carbon on the far left, on the first carbon. And so technically the name of this compound would be 1-pentanol. If you look at this interesting compound here, you see that in the hydrocarbon that I have circled in blue, the longest carbon chain has 8 carbons, and so it would be some kind of octane. However, if you put a hydroxyl over here, then the longest carbon chain does not possess 8 carbons. I should say the longest carbon chain does possess 8 carbons, but it's not the parent chain, because the parent chain has to include the hydroxyl. And so this would be carbon 1, 2, 3, 4, 5, and 6. You can see that over here we have a propyl group, and so this would be 2-propyl, 1-hexanol. And if you remember, rule number 5 here is said that you can put the locant for the hydroxyl just before the parent name or just before the all suffix. An application of that would be, you could call this compound 2-propyl 1-hexanol, or you could call it 2-propyl hexane or hexane 1-ol. Either one would be completely reasonable. Here you can see that we have a compound that has 2 functional groups in it. It has an alkene and an alcohol. If you ever run into a compound that has both an alkene and an alcohol in it, the alcohol takes precedence, and so you would call the compound an alcohol, not an alkene. So what do we seek to do? We seek to number the longest carbon chain in such a way that we give the hydroxyl the lowest possible number. So you can see that this is the correct way to do it over here because we have the hydroxyl on carbon 2. If you look at the second molecule, it's wrong because we have the hydroxyl on carbon number 6. This would be incorrect. The hydroxyl gets the lowest locant or lowest number possible despite the presence of pi bonds. If you're wondering how to name this bifunctional compound here where you have an alkene and an alcohol in it, you would call this compound 5,5,6-trimethyl. So let me scribble that down. This would be 5,5,6-trimethyl. 5,5,6-trimethyl, 6-heptene, and then 2-ol. That would be the name of this compound. Now, when we have the 6 in the heptene, that covers the double bond being at carbon number 6, and then we have the 2 in the ol, and that covers the hydroxyl being at carbon number 2. Here's another example of showing the hydroxyl locant being placed either just before the parent name or just before the ol suffix. I've already gone over this, but this is another example. You could call this molecule 3-pentanol or pentan 3-ol. They are both perfectly reasonable. There's nothing wrong with either of them. And of course, I would accept either one. If you study enough organic chemistry, you're bound to encounter cyclic alcohols. And if you're wondering about a cyclic alcohol, which carbon do I start numbering on? Well, whichever carbon possesses the hydroxyl group, that's always going to be carbon number 1. So this will always be carbon number 1. And then you're going to number the ring going clockwise or counterclockwise such that you give whichever substituents are on the ring the lowest possible numbers. So you can see that in this example here, that we start numbering counterclockwise. The reason why is because we end up with the hydroxyl, of course, on the first carbon and the dimethyl on the third carbon. If you had started numbering like this and going 1, 2, 3, 4 in a clockwise fashion, then the dimethyls would be at 4 and 4 instead of 3 and 3, and that would be incorrect. And so again, we want to seek to number the ring so that we give whatever substituents there are the lowest possible numbers. And of course, don't forget your stereochemistry. That goes all the way back to Chapter 5 in Organic Chemistry 1. Just a quick review here, if we take a look at this molecule, you can see that we have a hydrogen that's sticking out. That's the lowest priority group. We have the hydroxyl, which is the highest priority. And then between this carbon and this carbon, the carbon with the 2 on it is going to be higher priority because it's attached to a carbon that has carbons attached to it, whereas this carbon is only attached to some hydrogens and a carbon that has 2 hydrogens attached to it. So we go 1, 2, and then 3. So we go in a counterclockwise fashion, but since our proton, our lowest priority group, is coming out towards us, we reverse the stereochemical configuration from S to R. So make sure you're aware of how to designate the stereochemistry at a chiral center. Very important that you're able to do that in organic chemistry too. Common names are very common. We call them common names for a reason. Common names are used for alcohols all the time. For example, 2-propanol, this compound, we call that isopropyl alcohol. We also call that rubbing alcohol. If you've ever purchased rubbing alcohol at the drugstore. Another one would be 2-methyl-2-propanol. The common name for 2-methyl-2-propanol is tert-butyl alcohol. Another very common alcohol. And phenylmethanol, the common name for that is benzyl alcohol. In organic chemistry, whenever you see the word benzyl, benzyl just means that you have an aromatic ring and then you've got a CH2 attached to it. So that's what a benzyl group is. So you'd call that benzyl alcohol. Another thing that you've got to be able to do is to classify the type of carbon. And just like we saw with halides, alcohols are classified by the type of carbon that they are attached to. We can have primary, secondary, and tertiary alcohols. How do you determine whether you're dealing with a primary, secondary, or tertiary? Well, what you do is you look at the carbon that is directly attached to the oxygen of the hydroxyl group. We call that the alpha carbon. If the alpha carbon is attached to only one R group and 2 hydrogens, we call that a primary alcohol. If it's attached to 2 R groups and 1 hydrogen, we call that a secondary alcohol. And if it's attached to 3 R groups and no hydrogens, we call that a tertiary alcohol. Tertiary alcohols are kind of interesting because primary and secondary alcohols can be oxidized, whereas a tertiary alcohol cannot undergo oxidation. And that's something that we're going to see a little bit later in the class. What about phenols? We talked about them. How do we name them? Well, when an hydroxyl is attached to a benzene ring, again, we call that a phenol. We designate the carbon that has the hydroxyl attached to it as carbon number 1, and depending on the substituents, we number them in such a way that we provide the lowest possible numbers for those substituents. If you take a look at the carbon that the hydroxyl is attached to in this compound here, the reason we start numbering in a clockwise fashion is because we give the nitro 2 as a locant, and we give the chloro a 4 as a locant. If we were to go in the reverse direction, 1, 2, 3, 4, then we'd have our substituents at 4 and 6. And we want to give the first substituent the lowest possible number. A 2 is lower than a 4, and therefore the numbers that I have in blue are the correct numbers, and the ones that I'm erasing right now are wrong. Well, that's a lot of information to put together. Let's take that information and see if we can name some compounds. This first one is a primary alcohol. We have the longest carbon chain that we can see right here. And what we want to do is number that in such a way that we give the hydroxyl the lowest possible number. So we're going to start here with 1, 2, 3, 4, 5. You see that we have 3 methyl groups as substituents. We have a 2, 3, 4 trimethyl, 1 pentanol. In fact, I would scribble that down right now. We've got a 2, 3, 4 trimethyl, and you could call it pentan 1-ol. I'll just call it 1 pentanol. However, we have chiral centers at carbons 2 and 3, and so that means we're going to put 2 R or S and 3 R or S, and then 2, 3, 4 trimethyl 1 pentanol. And so now we need to designate the stereochemistry at carbons 2 and 3. I'm going to erase the numbers that I've got on there right now, and let's take a close look at carbon number 2. We have a proton which is going in back, and that is going to be our lowest priority group. We have this carbon as being our highest priority group. This would be our second highest priority, and this would be our third highest priority. And so we're going from 1 to 2 to 3, which is counterclockwise. And so this stereocenter is 2s. Now I'm going to erase all that, and we're going to do the exact same treatment for the next stereocenter. Again, we have our hydrogen going in the back. It is the lowest priority group. Then we have this carbon as being our first highest priority group. Then we have number 2, and then we have number 3. So we're going from 1 to 2 to 3. We're going clockwise, and therefore the stereochemistry or the stereochemical designation at carbon number 3 is R. And there you go. Now we've named the entire compound. Let me zoom out here. This would be 2s3r 2,3,4 trimethyl 1-pentanol or pentan 1-ol. Either one would be perfectly fine. The next one we see is a phenol, and you can see the phenol right here in the compound. And what we want to do is give the carbon that has the hydroxyl attached to it, the number 1. You can also see that there's a plane of symmetry through this molecule. If I just zoom in here, you can see there's a plane of symmetry right down the molecule. And so it wouldn't matter in this case if we went in the clockwise direction or counterclockwise. Either way, you're going to get the right answer. So we go 1, 2, 3, 4, 5, 6. You can see we have 2 ethyl groups, which means we're going to have to use the di prefix. So we have 2,6-diethyl phenol. And let's scribble that in here. We've got 2,6-diethyl phenol. Remember that numbers are separated by commas. Numbers and letters are separated by hyphens. All right, we've got one more. It's a cyclic alcohol, and it has a stereocenter in it. So let's take a look. This is some kind of cyclohexanol. We want to give the hydroxyl the lowest possible number. So we have 1. We're going to number this going counterclockwise so that we can give these two methyls a 2,2. If we went this way, they would be 4,4, so that would be incorrect. And thus we have 1, 2, 3, 4, 5, 6. So we have 2,2,4,4 tetramethyl cyclohexanol. Let's write that down. We've got 2, 2, 4, 4. Let me zoom out here. Tetramethyl cyclohexanol. And now we need to determine the stereochemistry at the only chiral center in the molecule. Remember that when you only have one chiral center in a molecule, you don't have to give it a locant. You don't have to call it 1R or 1S. All right, so let me just delete all that. We have our lowest priority group, which is our hydrogen in the back. So there we go. We have our highest priority group here, second highest priority, and we have our third highest priority. And we're going counterclockwise, and so that is S. Make the circle a little smaller maybe. And so there's the name of our compound. We have S2244 tetramethyl cyclohexanol. Not too bad. A little bit of practice in naming a linear alcohol, a phenol, and a cyclic alcohol. Okay, let's turn our attention to some commercially important alcohols. These are going to be some alcohols that show up all the time in organic chemistry. And the first one is the simplest possible alcohol that you can have, and that is methanol. Methanol is CH3OH. If we draw the complete Lewis structure, we have a carbon with 3 hydrogens attached to it. We have an oxygen, which has 2 single bonds, 2 lone pairs, and we have a hydrogen. So there's methanol, the simplest possible alcohol. And with a suitable catalyst, it says here that we make about 2 billion gallons of methanol per year from carbon dioxide and hydrogen. And methanol has a wide variety of uses. It is used as a solvent. It dissolves many different organic compounds. It can be used as a solvent in a reaction. It can be used as a precursor for chemical synthesis. That's just a way of saying it can be used as a reagent. And it can also be used as a fuel. In fact, there was a huge fire in the Indianapolis 500 in 1964, and it claimed the lives of 2 drivers. And at that time, the drivers were using gasoline. And so since gasoline burns with such a horrible, smoke and flames, that they actually switched over to methanol because it's easier to extinguish. and it burns with a much cleaner flame. In fact, if you've ever used fondue fuel, which is methanol, if you've ever made fondue, you'll notice that when methanol burns, it's a very clean flame. It's practically invisible. It's very difficult to detect it. Another name for methanol is wood alcohol. You might have heard that before. So wood alcohol. And the thing about methanol is that if you've ever heard of people making their own alcohol during Prohibition time, sometimes they would end up making wood alcohol or methanol by accident. And the problem with that is that although methanol can get you or get a human being intoxicated, it can also cause blindness and death. And so methanol is very dangerous for humans to consume, okay, extremely dangerous. The next one is ethanol. And ethanol that we think of in alcoholic beverages is produced from the fermentation of grains and fruits. And fermentation is nothing more than catabolism with no net oxidation. If you've studied biology, I'm sure you would have covered the concept of fermentation. So here's the formula of ethanol. It's CH3CH2OH. And industrially, ethanol is made via an acid catalyzed hydration of ethylene. So if we think about the molecule ethylene, which is nothing more than two carbons bound together it's just a hydrocarbon that has two sp2 hybridized carbons. If you treat that with H3O plus, I mean, there's no Markovnikov or anti-Markovnikov to consider, but you end up adding water to the molecule and you end up making ethanol. And so again, not all ethanol comes from corn or fermentation. A lot of it is just made from the acid catalyzed hydration of ethylene. And ethanol, like methanol, has many, many uses. A big one in organic chemistry is that is a solvent and can be used also as a reagent in chemical synthesis. Now, if you're wondering, well, if you work in a lab, does that mean you can get as much alcohol as you want, as much ethanol as you want? I suppose you can to a certain degree, and you can use that ethanol as a solvent. However, when we buy alcohol or ethanol for a lab, it's denatured. And what that means is that the ethanol is contaminated with small bits of toxic compounds like methanol, for example. And the reason why we do that is to prevent it from being used for human consumption and to avoid heavy taxes, because as everybody is probably aware of, alcohol that is fit for human consumption is highly taxed by the government. Anyhow, and I guess that was my next point. Ethanol that is suitable for drinking is highly or heavily taxed. So ethanol, a wide variety of uses for ethanol. And we're going to see it used as a solvent throughout organic chemistry too. The next commercially important alcohol is isopropanol. You might have heard me call that 2-propanol, and the bond line structure would be this here. This is also called rubbing alcohol. So isopropyl alcohol, isopropanol, 2-propanol, rubbing alcohol, they all mean the same thing. They all just mean isopropanol. And it is made from the acid catalyzed hydration of propylene. So if we think about what propylene is, let me just move this down here. Propylene is nothing more than propene. And if we take propene and we treat that with H3O plus, well, it's going to add in a Markovnikov fashion. And the rich are going to get richer, and we're going to end up with 2-propanol. It's used, again, as a solvent. It's also used as an antiseptic, and that's normally why people buy it at the drugstore to clean, wounds or something like that. And it's also used as a gasoline additive. So also found in gasoline, not just ethanol, but also isopropanol. Something that's interesting about alcohols is their physical properties. And this goes all the way back to probably the first chapter of organic chemistry when we discuss dipole-dipole forces, London forces, and of course, hydrogen bonding. And alcohols actually have quite high boiling points. Why? Because they possess a hydroxyl, which enables them to participate in hydrogen bonding. And I have a representation of hydrogen bonding between two alcohols shown right here in this picture. If you compare the boiling points of these three compounds on this slide, going from ethane to chloroethane to ethanol, well, ethylene is a completely nonpolar compound. It only experiences London forces, and thus it has a very low boiling point. When I get to chloroethane, of course it experiences London forces, but it also has a polar bond in it, and so it can experience a dipole-dipole force, which is stronger than a London force, and that increases the boiling point to about 12 degrees Celsius. So it increases it by 100 degrees Celsius or so. Then when I get up to ethanol, since it possesses that hydroxyl group that can participate in hydrogen bonding, it has the strongest of all the intermolecular forces possible for these three compounds, and therefore it has the highest boiling point of 78 degrees Celsius. So when we're talking about alcohols and phenols, that's something that we always have to keep in mind, that they are able to participate in hydrogen bonding. The next thing I want to discuss is the miscibility of alcohols in water. Now, there's a difference between miscibility and solubility. When we talk about miscibility, I think of it as mixability. And miscibility simply means that you can mix something in all proportions in another solvent. So when we're talking about miscibility in water, that means that you can mix the alcohol in water in any proportion with water. And when we have an alcohol that has less than 3 carbons, it is miscible in water. So 3 carbons or less is what I should have said. That means that you can mix it in any proportion. For example, we have methanol here, and methanol does possess a hydrophobic region, and it does possess a hydrophilic region, but the hydrophobic region is not that large, and the hydrophobic region can hydrogen bond with water, and that enables this molecule to be dissolvable or mixable or miscible in water in all proportions. However, once we get to an alcohol where we have a large hydrocarbon chain, and you can see here that we have 1, 2, 3, 4, 5, 6, 7, 8 carbons, so this would be 1-octanol. This molecule is practically insoluble in water. It does not mix with water. Why? Even though it has that hydrophilic region, that hydrophilic region is offset by the fact that you have a very large hydrophobic region, which prevents the alcohol from dissolving or being miscible in water in any proportion. Primary alcohols like methanol and ethanol, N-propanol and N-butanol exhibit antibacterial properties. Research indicates that the antibacterial potency of primary alcohols increases with increasing molecular weight, and this trend continues up to an alkyl chain length of 8 carbon atoms. So that would mean N-octanol, the compound that we saw on the last slide. You can see that it has the highest potency. Once you get past 8 carbon atoms, the potency decreases. That is, N-nonanol is less potent than N-octanol and N-dodecanol, etc., etc. Two trends explain this observation. An alcohol with a larger alkyl chain, meaning a bigger hydrophobic region, exhibits a greater ability to penetrate microbial membranes, which are composed of molecules with hydrophobic regions. According to this trend, potency should continue to increase with increased alkyl chain length, even beyond 8 carbon atoms. A compound with a larger alkyl chain exhibits lower solubility in water, however, decreasing its ability to be transported through aqueous media. This trend explains why the potency of alcohols decreases steeply as the alkyl chain becomes larger than 8 carbon atoms. A larger alcohol simply can't reach its destination and therefore has a low potency. The balance between these two trends is achieved perfectly for N-octanol, which has the highest antibacterial potency of the primary alcohols. Studies also show that chain branching decreases the ability of an alcohol to penetrate cell membranes. Accordingly, isopropanol is actually a less potent antibacterial than N-propanol or 1-propanol. However, isopropanol is used because it's less expensive to produce than N-propanol, which means the same thing as 1-propanol. And the difference in antibacterial potency doesn't justify the added expense of production. Many other antibacterial agents are specifically designed with alkyl chains that enable them to penetrate cell membranes. The design of these agents is optimized by carefully striking the right balance between the two trends that we're discussing, solubility and lipophilicity. Various chain lengths are tested to determine the optimal potency. In most cases, the optimal chain length is found to be between 5 and 9 carbon atoms. Take a look at the example of hexylresorcinol. If you take a look at resorcinol that I have drawn over here now, It is a weak antiseptic or antimicrobial, and it's used in the treatment of skin conditions such as eczema and psoriasis. Placing an alkyl chain on the ring increases its potency as an antiseptic. Studies indicate that the optimal potency is achieved with a 6-carbon chain length. Hexylresorcinol exhibits bactericidal and fungicidal properties and is used in many throat lozenges.